Let me start by giving you a little background on what you're going to see here. Our fictional demo company runs an e-commerce site, and they've recently refactored it to go cloud native by using microservices for the application architecture and containers for the underlying infrastructure. And the team that keeps the site up, the SRE team, are out for a team lunch. Yes, this was before COVID-19, when team lunches weren't an awkward combination of Zoom, Grubhub, and forced icebreakers. So in this scenario, they're just finishing up their dessert when Jenny, the SRE on call, gets paged. Jenny knows the alert is worth paying attention to because all of her alerts are backed by the reliable and intelligent analytics of the Splunk real-time metrics platform. So she pauses her conversation and looks at the message from Splunk on-call mobile. The alert shows that the number of purchases in the past hour has dropped, and the checkout completion rate is abnormally low. She knows it's truly an outlier because the alert logic takes into account the time and the day of the week as a dynamic baseline rather than simply using a static threshold. So to investigate further, she heads into the office and logs into Splunk Observability Suite from her laptop. She wants to begin by first understanding the impact of this alert she just received on the users. So she goes into Real User Monitoring view to see if there are any clues about problems that have occurred on the front end in the web app. She notices two issues that may be related to the checkout problems: a spike in the number of front-end JavaScript errors and high backend latency. She decides to probe further, as at this stage it's not clear if the two are related or is even causing the problems that she's noticing. She starts by taking a look at the endpoint latency and notices that /cart/checkout has huge latency, and so she clicks on it. On the right-hand panel, she sees that there indeed have been some spikes and that they're related to the fetch operation. Clicking into one of the exemplar traces shows that the latency isn't a front-end problem, but needs to be traced into the backend. Luckily, with the tight integration between RUM and Splunk APM, Jenny can click on the APM link to preview what is available to her. She could even follow the trace all the way through because she has access to full fidelity trace data with Splunk Observability. To make sure this isn't just a single outlier, Jenny clicks on the workflow link to see the aggregate behavior for this important transaction in their system. The performance issue that Jenny sees associated with a user action leads her to look at the full set of services backing the checkout action in APM. By just looking at the service map, she identifies that both payment service and the data store that backs the cart service, Galactus Postgres 98321, have errors that are identified by the system as root cause errors. In other words, the services with the most downstream errors contributing to a degraded experience. So switching to Splunk on-call incident war room, she adds the payment service and the cart service teams to the incident in addition to the SRE team that she's a part of. Since Splunk on-call handles all on-call schedules, she doesn't have to worry about which team member the alert is going to. Someone on the team is going to get paged. This brings Sarah, the cart service owner, and Andrew, the payment service owner, into the incident, and they go and look at their respective services. Sarah starts by keying in on Galactus Postgres 98321 in the service map. Postgres is a commonly used open source data store that backs multiple services inside of the company, and it runs on Kubernetes. So she wants to know if there's anything correlated with the errors being seen on the data store, so she selects it. Sarah goes to the bottom of the page to see information that is related to this service, like what infrastructure it runs on, what alerts it has, whether there are any error logs associated with it, and so on. She decides to check on the first item just to eliminate infrastructure problems as a source of issues. When she does that, she doesn't notice anything out of the ordinary. There was a code push, and so the pods running in the service are relatively new, but everything seems to be within normal bounds, and the error messages she's seeing don't indicate anything that would explain the high latency. Meanwhile, Andrew is looking into payment service, a custom microservice that's been instrumented using OpenTelemetry, the new standard for unified metrics, traces, and log data that Splunk is a leader in contributing to. Thankfully, even without having to dig into individual traces, Andrew can see and aggregate trends in his errors. He notices that most errors are from the production environment. He can then dig deeper with Tag Spotlight, which takes advantage of infinite cardinality to see how his requests and errors are distributed by each tag and value. This not only allows him to identify the root cause, but also get a feel for the radius of impact. Here the versions point to a problematic deploy, and it seems like all tenant levels are affected. He can now narrow his investigation to the version of the code and dive deep into a specific trace. With Splunk full fidelity approach, Andrew is confident that he has had the end-to-end trace when he needs to dig deeper. Andrew now notices a trace that is showing some unexpected behavior, so he looks for additional information that has been collected while this is going on. Given that we're using OpenTelemetry, all the metadata he needs to correlate the traces and relevant logs is available. So he simply needs to click on the highlighted trace ID to look for related logs. In the log view, he sees a number of log lines that are related to the selected trace ID and notes that some of them are errors. The message indicates that there was a failed payment attempt, but also that the checkout seems to have eventually gone through. To investigate further, Andrew clicks on one of the errors to see the details that are captured in the log line. What he sees appears instantaneously suspicious to him. The failed payment message also indicates that an API token being used is invalid, and the name of the token is a dead giveaway. It's a test and not a production token. To confirm his hypothesis, Andrew selects the message, adds it to the filter along with the service by its name, and clears the trace ID filter so that he can broaden the dataset to include all of the logs with that message for the payment service. He then switches to Visual Analytics to group by version number and then widens the selected time range. He instantly sees that v350.10 is correlated with all of the errors that are being seen. Luckily, this is only happening in a subset of the environment, since his company does canary pushes to see how new code is doing before it gets promoted to the environment as a whole. Since there's obviously something wrong here, he decides to revert the code back to a known good state while he hunts down the right token to use. To confirm that this is all working, he watches the live tail to make sure the failed payment messages present in his logs previously are not making a reappearance. As the code gets rolled back, the errors die down and the latency for the checkout service goes back to normal levels. Andrew doesn't even have to go to another tool to see this. He gets the notification on his laptop that it has cleared.